So we are ready to prove one of the key properties of determinants. This is one of the reasons why we care about determinants, why we've spent so much time learning about them. A square matrix is singular if and only if the determinant of that square matrix is 0. So first off, remember singular is just another way to say not invertible. Okay, so a square matrix is singular or not invertible if and only if the determinant of the matrix is 0. So you can find out if a matrix is invertible or not just by taking its determinant. Okay. Okay. So we're going to prove this two ways. We're first going to do the rigorous math proof, but then I also want to provide a geometric argument, some geometric intuition on why this is true. So we're going to start with a square matrix A. And so to determine whether A is singular, generally we need to find the reduced row echelon form of matrix A. Remember that if A is invertible, then the reduced row echelon form of A is equal to the identity matrix. Okay, so if A is invertible, then the reduced row echelon form of A is equal to the identity matrix. So if we can find the reduced row echelon form of A, we can immediately see whether A is singular or whether it's invertible. Okay? All right, so how do we actually go about finding the reduced row echelon form of a matrix? Well, we need to apply elementary row operations. Specifically, there exists a set of elementary matrices such that if we multiply matrix A by these elementary matrices, we can get the reduced row echelon form of A, because multiplying by an elementary matrix is the same as applying an elementary row operation. Okay, so there's a set of matrices that we can multiply, set of elementary matrices we can multiply that'll give us the reduced row echelon form of A. Okay, so the determinant of this product of elementary matrices with A is going to be equal to the determinant of the reduced row echelon form of matrix A. Right? But we just proved an important lemma about elementary matrices. That is, remember, if you take the determinant of an elementary matrix times another matrix, you can separate the determinant of the elementary matrix and the determinant of the other matrix, and then multiply those determinants together. Okay, so we could repeatedly do that right here, and then just take the determinant of each elementary matrix on its own, and then multiply that by the determinant of A. All right? So that's our strategy here. Now, if A is a singular matrix, then the reduced row echelon of A, the reduced row echelon form of A, is not the identity matrix. But if it's not the identity matrix, because it's a square matrix, that would mean there is a row of zeros, that the reduced row echelon form of A has a row of zeros. And we've seen that if a matrix has a row of zeros, the determinant of that matrix that has a row of zeros is itself 0. Okay? So this is equal to 0. Now on this side, we have a product of a bunch of determinants that is equal to 0. Remember, if you multiply two things together and you get 0, one of those things has to be 0. If I take two numbers A and B and I multiply to get 0, either A has to be 0 or B has to be 0, or potentially both. Okay? So that means because the determinant on the right-hand side is 0, one of these determinants has to be 0. But we know the determinants of elementary matrices. They're easy to calculate, and none of them are 0. Either I'm going to swap two rows, in which case the determinant will just change signs from 1 to -1, or I'm going to multiply by a non-zero constant, in which case the determinant of the elementary matrix is just k times the determinant of the identity, which would just be k times 1, or just k. Or I add a multiple of one row to another row, and that doesn't change the determinant at all. So it'd just be equal to the determinant of the identity matrix as 1. So the determinant of elementary matrices will never be 0. So that must mean the only other determinant that's left that could be 0 is the determinant of A. And so we conclude that if matrix A is singular, then the determinant of matrix A must be 0. Okay, now we've only proven one half of the proof here because it's an if and only if. Okay, so we have proven if the matrix is singular, then the determinant is 0. Now we have to go the other way around. If the determinant is 0, we need to show that matrix A is a singular matrix. Okay, so suppose the determinant of A is 0. Well, then the determinant of the reduced row echelon form of A, again, it's equal to the determinant of a bunch of elementary matrices times the determinant of matrix A. But we just said the determinant of A is 0. So we'd have 0 times a bunch of stuff, we get 0. So the determinant of the reduced row echelon form of A must be 0. But that must mean that the reduced row echelon form of A is not the identity matrix, because the determinant of the identity matrix is 1, not 0. In order to be invertible, the reduced row echelon form of A has to be the identity matrix. Since it isn't, that must mean A is a singular matrix. Okay? So this gives us a way to find out if a matrix is invertible or not by just taking the determinant of the matrix. If the determinant of the matrix is 0, then the matrix is singular. It does not have an inverse. But if the determinant is anything else, anything other than 0, then the matrix is invertible. Okay? So that's the rigorous mathematical proof. But as promised, I also want to cover a geometric argument for why this is true, and it'll give us, I think, a little bit more intuition on what's going on here. Okay? So remember one way to think about the determinant of a matrix. So let's say a matrix with column C1, C2, C3. Is the measure of the region determined by those vectors, those column vectors. So in the case of 2 vectors, you would get a parallelogram. In the case of 3 vectors, kind of like I have here, you would have a parallelepiped. So this would be the volume of the parallelepiped determined by C1, C2, C3. Okay? So with that interpretation in mind, let's think about this. Okay? So I have 2 vectors, and I have shaded the volume, or I'm sorry, the area, we're in 2 dimensions, the area of the parallelogram that is determined by those 2 vectors. So I can move where the vectors are, and I would get a different parallelogram. So the determinant of the matrix, where these two vectors would be the column of the matrix, the determinant of that matrix would be equal to the area of this parallelogram, right? And so I could have all kinds of parallelograms with different areas. All right. But what would it take to get in a parallelogram with 0 area? It wouldn't really be a parallelogram yet then. But how would we manipulate this so that the region would have 0 area? Well, if I pull this back, so that the two vectors line up, then the parallelogram, if you want to call that, determined by the two vectors has zero area. And so the determinant of the matrix with columns equal to these two vectors would be zero also. And what do we see here? The two vectors are in a line, which means they are linearly dependent. They are linearly dependent. So we know that if we, with linearly dependent vectors, if we put them in a matrix, if we use elementary row operations to get it into reduced row echelon form, we would have some free variables, right? Not the identity matrix, which means the matrix would not be invertible. We have linearly dependent vectors here. All right, let's see example in 3D, just to give you one extra dimension. This one's a little bit harder to manipulate by hand, but you see you have three vectors here in three-dimensional space. And also you see the parallelepiped determined by those three vectors. Okay, the determinant of the matrix, where the columns of the matrix are equal to these three vectors, the determinant of that matrix is equal to the volume of this parallelepiped. All right, but let's see what happens when we make the vectors linearly dependent. I'm going to make one of these vectors linearly dependent with the others. Okay. Notice that the three vectors lie in a plane, and now our parallelepiped has kind of gone flat, right? It just lies in a plane now. Now notice it still has area, but it doesn't have volume because it has no height, no that extra dimension collapse. The volume of this shape now is 0. And so the determinant of the matrix, where the columns of the matrix are equal to these three vectors, the determinant of that would be 0. And that makes sense. These vectors are linearly dependent. And so if we reduce that matrix to reduced row echelon form, we know that we would not get the identity matrix. We would have a free variable in there, right? We would have a column without a leading entry. So this gives you an idea of what happens in 2D and 3D. The same geometric interpretation can apply to higher dimensions also. If you look at the measure of the higher dimensional equivalent of a parallelepiped.